Hey folks, this is Major Jones here to talk to you about the implementation of the control unit. So we're going to finally see how the sausage gets made. Today, our objectives are threefold. We're going to describe the operation of the microprogrammed finite state machine with sequencer that's inside the control unit. I'll show you the reasoning behind the state numbers because they look a little weird. And lastly, we'll describe the control store. Let's get started. Okay, so actually, I'm gonna jump back a lesson. If you recall from our last lesson on microprogrammed finite state machines, right? We learned that the hardwired finite state machines maybe are a little more efficient, but ultimately they're hard to change. So a microprogrammed finite state machine that uses like this memory, almost like a lookup table kind of, to decide what our next state is, allows us to sort of change that memory and possibly change the operation of our finite state machine. So that's a good thing. We're going to use that in the LC3. And recall that the without a sequencer, this memory can get rather large. And so, by way of example, recall from this is our kind of our close up of our first look at of the control unit. We've got 10 bits effectively coming into our control unit from the LC3. So these are various status signals that affect which state we go to next. Additionally, J here is sort of like our next state. And there are 6 bits that we need to encode which state we're in because there are that many states in our finite state machine. So if we were to do this with just sort of a normal, microprogrammed finite state machine, we have our 10 bits of input plus our 6 bits of state. That's 2 to the 16th rows that we would possibly need in this memory to implement this finite state machine. That's as big a memory as the LC3 supports just on its own, like for the entire computer operation. That's just like super egregious. So we are not going to do this. We are going to use the technique of microprogramming with a sequencer. So we're gonna sort of change. We're gonna encode this finite state machine so that each row of our sort of memory is also sort of defines what transition we are looking for. So let's take a look at how we do that. So this effectively, if I were to sort of expand this out, right, it would look here. So the control store down here, this is basically our memory. That's the memory portion of our microprogrammed finite state machine. And then this little box down here is representing basically our register that holds sort of the current signals that are coming out of our finite state machine. And then the micro sequencer part, you can see up here, takes some information. Here, I'll see if I can kind of zoom in just a little bit. It takes the J signal, which is sort of our current or next state. It looks at the condition. So this is sort of the condition code that determines, which signal we might branch on. And then we have a couple of different signals that potentially change the way our control. The way our finite state machine sort of is executed. And then we also have a little multiplexer down here. So the one really nice thing about this that the designers of the LC3 did is to say, okay, well, if we have opcodes for each of the instructions, so you know what, after we finish our decoding, if we've determined that what we're which instruction we're executing, we'll let that opcode become the state number. So for instance, let me see if I can pull this up real quick. Okay. So let's take our AND instruction. ANDing has the opcode 0101, right, which is decimal 5. If we look at where do I want to go next? I want to stay here. If we look at our state machine, you'll notice that the decode state is state number 32. And the ANDing is state 5. So the numeral 5 here, state number 5, matches the opcode. Okay, so that's kind of the one nice thing. We are, if we happen to be decoding an actual instruction, then the next state is just whatever our opcode is. All right. But for basically every other state, we are going to use this as our sort of our sequencer. And the way this works is this. Condition is a 3-bit code that that specifies what we're waiting on, basically. And you can see here I've got 6 specific signals I can sort of trigger on. So I can trigger on if there's an access control violation, or if there's an interrupt signal, or if there's a branch enabled, if that bit has been set. And And then the state numbers are situated. You can see these are being ORed together. They're situated such that if my that my next state, if the condition is false, can be ORed with whatever bit position I'm looking at here to get to the next state that's true. So, for example, let's go down here. You can see this is a little kind of snapshot of our state machine. And so in this state here, this is state number 28. And so this is, if I'm not mistaken, this is part of the fetch phase. What we're doing is we're loading the memory data register with our instruction, and we have to wait for the ready bit from the memory to tell us that that the memory data register has been loaded. So so we have a transition back to the same state as long as we're not ready, and as soon as we are ready, we move to state number 30. All right. So the state numbers were chosen very specifically. 28 in binary looks like this: 0, 1, 1, 1, 0, 0. And since we're waiting on the ready bit, you'll notice up here that the R, the ready bit, is in bit position 1. So if that were to be true, then the result of these AND gates would be 0, 0, 0, 0, 1, 0. The follow-on state, as soon as ready bit is true, is chosen to be 30 very specifically because if we OR together these two numbers, we get 0, 1, 1, 1, 1, 0, which is 30. So so based on this circuit right here, right, we would, if we were in state number 28, J5 through J0 would have that binary value 28. And our condition values would be selecting for this ready bit here. If the ready is false, then the output of this AND gate is just 0. We OR whatever's in J1 with 0, and we get whatever would be sort of our next state, assuming the condition were false, which means we stay in state 28 in this case in specific. And as soon as the ready bit becomes true, the output of this AND gate is a 1. We OR J1 with a 1, and that will change the next state value effectively to 30. And that'll transition this finite state machine here into state number 30. So, okay. So let me show you. I feel like I should show you. Let me zoom out. The condition codes. You saw them. Okay, here they are. You saw them there, right? I've got condition 6 means I'm testing for my access control violation. Condition 1 means I'm testing for is my memory ready. The only one that's kind of not listed there, it's kind of implicit, is if my condition bits are all 0, then that's effectively an unconditional jump. You can imagine here that if all my condition bits are 0, then none of these AND gates are going to return a true, and we, regardless of what's going on in the system, we will branch or jump to whatever state is encoded in J5 to J0. So then it is the control store is our memory that holds all this information. So this is a big table that effectively is encoded in this memory right here. We have 2 to the 6 rows, so 64 rows, and 52 bits wide. 42 of those bits are control signals. 10 of them are the signals that we need to figure out where we're transitioning to next. J is sort of our next state, the 3 bits for our condition, and 1 bit to say if we are actually decoding something and we're using our opcode as our next state or not. And so so the control store starts off sort of with that information. And for this example here, in state number 28, I already would be 0 because I'm not decoding. My condition should be 1, okay, because that is the code for waiting for the memory ready condition. Excuse me, I'm trying to back up to where that is. Right, there it is. Condition 1 means I'm waiting for my memory, and that matches this diagram here, right? If two conditions, the bits are 0, 0, 1, 0, 0, 1 matches these rows, so this is sort of turning on the ready bit. And then J, my next state, is encoded as 0, 1, 1, 1, 0, 0. That was 28 when ready bit is false, effectively telling my state machine to sort of stay in this bit or in this state until ready becomes true. And when it does, this bit will become a 1. And so the next state when it becomes true is state number 30. And what comes to the right of these signals that sort of define the state machine are all the control signals, the 42 control signals that that control my LC3. So you can see, across the top of this diagram here, effectively, I have, my RD, my condition, my J, and then all of the control signals that run my LC3, load in my memory address register, where's gate ALU. I've got my PCMux control bit. So, these get specified for every state. And effectively, that's exactly how my the control unit for the LC3 works. So it's a micro-programmed finite state machine with a sequencer. And that means we've got a control store that sort of specifies not just the control signals, but then also what's my next state, what condition am I sort of branching on, and in this case, am I trying to decode? Am I using the opcode for to figure out what my next state is? All right. Hopefully that was a good introduction. That's all I got. I'll see y'all next time.